Most people treat op amps like black boxes, but in reality, every behavior, gain, bandwidth, distortion comes from simple relationships. So, in this video, we are not just simulating an inverting amplifier using the 741. We are breaking it down from equations to real world behavior. Let's get started. So, what is an inverting amplifier? An inverting amplifier is a configuration of operational amplifier when the input signal is applied to the inverting terminal and the non-inverting terminal is grounded. Because of the high gain of the op amp, the inverting terminal is maintained at a virtual ground, meaning its voltage is approximately zero. This forces the current through the input resistor to flow entirely through the feedback resistor, and that's where the entire behavior of the circuit comes from. If I have to explain you with this system right here, you can see that there is no current flowing in the op amp. You can see 0 and 0 at both the terminals, and the whole current is fluctuating, or you can say flowing, between the feedback loop. This is the inverting feedback configuration. Now, deriving the gain expression, let's break that down and make this circuit feel more logical than voodoo magic. The current through the input resistor is Vin divided by Rn. Since no current enters the op amp, which is confirmed by 0 amp here, the same current flows through the feedback resistor, which you can see right here, this loop entering. So the output voltage becomes negative of the current multiplied by Rf. Here Rf is 2 kilo ohms, and if you see the input voltage is given by orange color line, it is of 2 volt, and the output voltage is given by green color line, which is of 4 volt. So if you multiply 2 volt with 2 kilo ohm, or the ratio which is 2 kilo ohm by 1 kilo ohm, which gives you 2, so you get a 4 volt peak, which you can see here. Now, but there is a catch, and let's see that. The current through the input resistor is Vin divided by Rn. Since no current enters the op amp, the same current flows through the feedback resistor. So the output becomes negative of the current multiplied by Rf by Rn. Right, because there are many relations which I have given here in this, uh, you can say, formula book, which you can use to derive this relation, such as the AV upon V node equals to AV upon Vin. And that directly gives us the gain equation, which is AV equals to minus RF upon Rn. Interpreting the formula, the negative sign indicates the 180-degree phase inversion. You can see this waves have been phase shifted by 180 degrees. And the ratio of the resistor controls how much amplification we get. Currently we are using 1 and 2 kilo ohms. So if I use 4 kilo ohms, let's say, in the output feedback, so I should get, okay, we will use 3 kilo ohms so that I don't have to change the graph videos a lot. And let's try to squeeze this up. So you can actually see that we are getting a 6 volt peak here, which is right above the 5 volt marker, and in the bottom one we are still getting a 2 volt peak, so that is 3 times the amplification. which is happening. If you can see clearly, this can be seen. So this is how you control the negative feedback amplification using the ratio of RF and RL. So in my previous configuration, I have used 2 kilo ohms for getting this 4 and 2 volts output. Let's get that to 2.2 kilo ohms so I can make my calculations a bit easier on the graph. Now, currently I am using every circuit. This is a very nice software. I'll pin down the link below. But for more detailed analysis, we have to use LTspice. This is a good software if you want to clear out your basics or you want to visualize your um, circuits very well. Now let's move on to LTspice for the transient analysis. I have my LTspice here. Now let's verify this circuit with transient analysis. I just have to change one thing. I'll change the amplitude of the power supply to 2 volts so that we can see a 4-volt output. Now, before putting the transient analysis, I want the stop time to be 2 seconds. I want to start saving the data as when the circuit starts, and we can go with minimum time span of timestamp of 0.1 seconds. Okay, and let's start the analysis. Okay. So if I see my analysis here, okay, I have used 220, 2, 2.2K, but if I just use a 2K, I should get a clean multiple of 2 waveform here. And we'll simulate that again. Okay, that is a bit problematic. Sometimes uh, LTspice gets you the current simulations which you don't want actually sometimes. Okay, if we zoom in properly, this much would be great. This is better. So here you can see my input is 2 volts and my output is 4 volts. Now we verify this clearly using the transient analysis. We apply a sinusoidal signal and observe both input and output. The output waveform is clearly inverted, you can see, confirming the phase shift, and the amplitude is higher than the input, confirming the amplification. And its amplitude is higher than the input, confirming the amplification, but the factor is 2, which also confirms that the amplification or the gain is 2. So this circuit is behaving exactly as predicted by the gain equation. Now, there is a very crazy thing which happens further. This is where the theory starts breaking. But real systems don't stay ideal for long. When we increase frequency or input amplitude, the output no longer follows perfectly. The gain reduces and distortion appears. This happens because real op-amps like LM741 have internal limitations. Before we do the AC analysis and find that out, I want to show you a live animation so that you can get a clear view of what I am talking about. So if I increase the amplitude here to 10 volts or greater than 10 volts, you may see that input is still a sine wave, but output is more like a square wave plus sine wave. There is some sine wave plus a square wave factor. Okay, now if I bring back the amplitude to 2 volts and frequency, if I increase the frequency more, to let's say 100 kilohertz or more, now you can see this is some kind of distortion which is coming in. Okay, I'll slow down the frequency a bit. You can see there is a bit of distortion. This is because the internal limitations of op-amp makes it do this. So for the op-amp to stay in the ideal zone, or to stay in a perfect zone, we need to calculate the bandwidth. And for the bandwidth, we have to do AC analysis. So now let's do the AC analysis of the same. To do the AC analysis, we move this transient analysis statement and add a AC analysis statement. Basically, AC analysis, here we plot gain versus the frequency graph. At low frequencies, the gain remains constant and matching our calculated value. But beyond a certain frequency, the gain starts to drop. So now we have to do the AC analysis. You have to first go to this configure analysis option and then select AC analysis. Then select time sweep, set it to decades, set number of points to 10, start frequency you can set around 500 and stop frequency you can set around 30 kilo ohms. This is totally up to you. Paste it anywhere and start. Okay, one more thing there I forgot to tell you is that you have to set your voltage input voltage source as a AC source, because this will sweep across this domain. So starting frequency will be 500 hertz, then it will end with 30 kilohertz frequency. So what will happen, the AC or this voltage source will constantly change its frequency to a new frequency. So for that you have to set it to none, and in this you can just set it to AC like that. You just set it to none and it will do the matching. Yeah, by the way, you just have to enter the amplitude. So I'm entering 2 volts still. So it comes out to be AC2, and now we get, which is here, 10 AV. Now we have done everything, and I'll just give you some high value pointers. This leads to an important conclusion. If you increase gain, bandwidth decreases because the gain bandwidth product remains approximately constant for a given op amp. Now, so in this experiment, we didn't just simulate a circuit, we derived its behavior, verified it using transient analysis, and explored its limitations using AC analysis. From equations to waveform, everything connects. And that's how you move from using circuits to understanding them. Thank you.